multiplying and dividing complex numbers. Now, you can apply the modulus argument rules for multiplying and dividing complex numbers to numbers written in exponential form. So, if you remember from previous videos, if we have any two complex numbers, say z1 and z2, then the modulus of z1 times z2, that's equal to the modulus of z1 times the modulus of z2. And if we have the argument of z1 times z2, that's equal to the argument of z1 plus the argument of z2. If we have the modulus of z1 divided by z2, that's the same as the modulus of z1 divided by the modulus of z2. And if we have the argument of z1 divided by z2, that's equal to the argument of z1 take away the argument of z2. And we proved these results using the addition formulae for cos and sin, and when we did that we came up with these results over here, and that's assuming that the complex numbers z1 and z2 can be written in this form: r lots of cos theta plus I sine theta. Now we can apply these rules to numbers in exponential form, and if we do that we have the following results. So if we have z1 equaling r1 times e to the I theta 1, and if we have z2 equaling r2 times e to the I theta 2, then z1 times z2, that's going to equal r1 times r2 times e to the I lots of theta 1 plus theta 2, and if we have z1 divided by z2, then that's the same as r1 divided by r2 multiplied by e to the I lots of theta 1 minus theta 2. And you cannot automatically assume the laws of indices work the same way with complex numbers as with real numbers. This result only shows that they can be applied in these specific cases. Example number 6. For part A, we have to express 2 times by e to the power of pi I over 6 times by root 3 times e to the power of pi I over 3 in the form x plus iy. Now if we use the rules which we mentioned here, we've got z1, which is this result here, z2, which is equal to this result over here. So we need to first of all multiply r1 and r2 together. In other words, we need to multiply the 2 and the root 3 together. So if we do that, we have 2 times by root 3, which is 2 root 3, and then we have this multiplied by e, and then we raise this e to the power of I, and then what we do over here is simply add the powers as we see in the rule over here. So we have I lots of pi over 6 plus pi over 3. So if we tidy this up, you can see here pi over 6 plus pi over 3, that's pi over 2. So we end up with 2 root 3 e to the power of pi I over 2. Now we need to express this result in the form x plus iy, and to do this we can use the result we had over here. We know what essentially this new r is, we know what the new theta is. So if we substitute those into this equation over here, we can then simplify the result. So we have our new r, which is equal to 2 root 3, and then we multiply this by the cosine of pi over 2, and then we add on I times by the sine of pi over 2. So if we tidy this up, we have 2 root 3. Cos of pi over 2, that's just 0. I times by the sine of pi over 2, that's just 1 times by I. So if we expand and simplify all this, you can see we have 2 root 3 I as our final answer. You can see here we have z equals 2 plus 2i. We have the imaginary part of zw equaling 0, and we also have the modulus of zw equaling 3 times by the modulus of z. And our goal in this question is to use geometrical reasoning to find the two possibilities for w, giving it answers in exponential form. So how do we go about doing this question? Well, first of all, we know what z is over here. So with this, we can find both the modulus of z and the argument of z. So if we use these results, we have the modulus of z, which is equal to 2 squared plus 2 squared square rooted. We have over here 4 plus 4, which is 8, square root 8, that's 2 root 2. And for the argument of z, clearly you can see, to work out the argument, you'll first of all notice z lies in the first quadrant, so the argument of z is equal to the inverse tan of 2 over 2, which is pi over 4 radians. We'll leave that alone for a second. What we also know is that the modulus of z times by w is equal to 3 lots of the modulus of z. So if we use this result, the modulus of zw, using what we mentioned over here, the modulus of zw, that's equal to the modulus of z times by the modulus of w. And we know that this result is equal to 3 times by the modulus of z. So we have the modulus of z times by the modulus of w, which is the same as the modulus of zw. This is equal to 3 lots of the modulus of z. In other words, the modulus of w is equal to 3. Now, what does this mean over here? Well, we can't do much with this for now, but what we do know is that the imaginary part of ZW is equal to 0. So let's just write this down. We have the imaginary part of ZW, which is equal to 0. So let's attempt to sketch the imaginary part of ZW. If we have an Argand diagram as shown over here, if the imaginary part of ZW is equal to 0, that means the complex number ZW lies on the real axis over here. And of course we know from the question that we have to find two possibilities for W. So either ZW lies over here somewhere, or it lies over here somewhere. So let's just mark these on. We have ZW1 possibly going over here, because remember the imaginary part of ZW is equal to 0, so it lies on the real axis, or alternatively, for the same reason, ZW2 lies over here. Okay, so these are our two possibilities. And I think over here, what we can say from here then is the imaginary part of ZW implies that the argument of ZW is either equal to 0, in which case it lies over here, or it equals pi, in which case it lies over here. So what we can now do as well is show the complex number Z on this Argand diagram. So if we do that, pi over 4, that looks something like this. So here is the complex number Z, which is equal to 2 plus 2i. So what does this mean over here? Well, we know that when we find the argument of two complex numbers multiplied together, we add those arguments together. So what we can hopefully see from here then is the argument of Z times by W, this is equal to the argument of Z, okay, plus the argument of W. And this can either equal 0 or pi. Well, we know over here that the argument of Z, we've just found that to be pi over 4. So we have pi over 4 plus the argument of W either equaling to 0 or pi. Well, of course, if the argument of W plus pi over 4 is equal to 0, that suggests to us that the argument of W is equal to, hopefully here you can see minus pi over 4, or if the argument of W plus pi over 4 is equal to pi, hopefully here you can see that the argument of W is equal to 3 pi over 4. Okay, so we've got two possibilities for the argument of w. Okay, so how does this help us? Well, what we can now do is state the two possibilities of the complex number w, because we know the arguments and we also know that the modulus of w is equal to 3. So therefore, hopefully you can see w1, that will equal 3 e to the power of minus pi I over 4, and w2, that's equal to 3 e to the 3 pi I over 4. So these are our two possibilities for w. Number 7, we have to express 2 times by the cosine of pi over 12 plus I sine of pi over 12 over root 2 times by the cosine of 5 pi over 6 plus I sine of 5 pi over 6 in the form re to the I theta. So to do this question, we begin with the 2 times by the cosine of pi over 12 plus I times by the sine of pi over 12 divided by root 2 times by the cosine of 5 pi over 6 plus I sine of 5 pi over 6. So, if we write this in exponential form, you can see here for this top complex number on the numerator, we've got r, which is 2, and theta, which is equal to pi over 12. So we have here 2e to the power of pi I over 12. And on the denominator, we've got r, which is equal to root 2. And then we multiply this by e, and you can see here the power, the value of theta is 5 pi over 6. So we have root 2e to the power of 5 pi I over 6. So we need to use the rule over here when dividing complex numbers. So to deal with this, we have 2 over root 2, so that is the r1 over the r2. And then we multiply this by e, and we raise this to the power of I, and then we subtract the arguments. So we have here I lots of pi over 12 minus 5 pi over 6. So if we tidy all this up, 2 over root 2, that's just root 2. And we multiply this by e, and then pi over 12 minus 5 pi over 6, you'd find that to be minus 3 pi over 4. So we subtract off 3 pi I over 4. So this is our final answer.